Hello, students. In this video, we will be discussing de Broglie's postulate that electrons behave as waves. So this is it's really kind of an interesting topic because it's kind of the opposite of the photoelectric effect. In the photoelectric effect, we were seeing how light behaves as particles with the ejection of electrons, and now with de Broglie's postulate, we'll see how particles behave as waves and have wave-like characteristics. So de Broglie predicted that the wavelength of a particle was inversely proportional to its momentum. Because it is so small, the wave characteristics of electrons or things at the microscopic scale are significant. So we have to take into account this wave characteristic. So the wavelength of this extends to all matter, okay? The wavelength of all matter is equal to Planck's constant divided by its momentum, which is mass times velocity, sometimes seen as rho. The symbol looks a little bit different than that, but it looks like a cursive P or a symbol of P. So we're going to use de Broglie's postulate, and we're going to actually calculate an example of this. So let's calculate the wavelength of an electron traveling with a speed of 2.65 times 10 to the 6 meters per second. That's fairly fast. Okay, so we'll use again Planck's constant. Now we have the velocity, we have the speed, it's given to us. What we are missing here is the mass. So what we need to get is the mass of an electron. Now, typically, this is provided in a lot of tables for you. This is not something you're expected to memorize. If it wasn't given directly in the problem, you'll be able to look it up, or it'll be provided in the table for you. But once we get that, it's 9.11 times 10 to the negative 31 kilograms, which is substantially larger than an AMU, which is roughly 10 to the negative 27 kilograms. So we can see that an electron is substantially smaller. But we're plugging this in using our constant for Planck, and we convert, if you recall, Planck's constant is units of joules per second. What we are doing is we're converting the joules to the kilogram per meters squared per second squared, which we see right here. And we see that the kilograms cancel, one of the seconds can cancel here, but then when we use the velocity, which is meters per second, now the other per second cancels, one of the meters canceled, and I'm left in units of meters. So I get 2.74 times 10 to the negative 10 meters. And again, 10 to the negative 9 meters would be a nanometer. So this wavelength is substantial. And the reason you don't see a lot, a discussion of this is because we tend to think of things at the macro level. So like a baseball. And when we extend, de Broglie's postulate to large objects, what happens is with really large masses, so when the mass is really large, this denominator becomes really big, and what happens is the quotient ends up being so small that the wavelength, you just can't see it. So it's significant when we get to the micro scale, such as electrons and things of that nature. And again, the units of the answer are in meters. That's correct. The magnitude is small, but it is substantial because when we're talking about wavelengths of electrons, with it being close to a nanometer, it falls within that electromagnetic spectrum, and this is a reasonable answer. So I hope you like this video. If you have any questions, let me know, and I'm glad we were able to apply de Broglie's postulate. Thanks for watching.